So hello and welcome student to the today's lecture, and of course my name is MA412 linear linear algebra, and this is lecture number 13. Okay, so today we will discuss a very important and new idea. This is one of the central idea of linear algebra. Okay, and this is called diagonalization. Diagonalization. Okay. Okay. So let me first define it, and then we will say that what is the meaning of that diagonalization. Okay. I mean there are various way of defining it. There are various equivalent form. Maybe I will define it by two equivalent form, and then we will show that there exists many other equivalent form. Okay. And why this is important? Because okay, so let us define, then we will understand. Okay. So let um, so I'm assuming that V is finite dimensional. So let V be capital V be a finite dimensional so vector space over some field over some field F. Okay. Okay, then and you choose a linear operator T belongs to LV, some linear operator. Okay, but then the following are equivalent. Then the following are equivalent. Okay. So I will just start with two, and then later I will discuss one by one other forms of equivalent forms. Okay. So number one is what that number one is TB is a diagonal matrix I hope we know what is the meaning of diagonal matrix. Matrix for some basis B of V, okay, over the field F. Okay, so there is some basis with respect to that the matrix representation of T is a diagonal matrix. Diagonal means the diagonal elements are non-zero. I mean, diagonal element can be zero, not do anything, but other than diagonal, everything is zero. Diagonal can be zero, non-zero, anything. Okay. And number two is what? V V has a basis. Has a basis consisting of eigenvectors of T. Okay, so I just wrote two statements that either T is a diagonal matrix for some basis B over F, or we have a B as a basis, the basis element of the basis of the eigenvectors of T. Okay, basis means basis over the same field type. Okay, so in any such cases, so in any of these cases, we say that T is diagonalizable. Diagonalizable. Okay. If any of this, if any of one or two, whatever, uh, happens. Okay, so we call this diagonalizable. Okay, so when does a linear operator is called diagonalizable? If the vector space consists of eigenvectors of that linear operator T, or vector space it has a basis consisting of that, or you can have a basis that with respect to that the T, the matrix representation of T will be diagonal matrix. Okay, so these are actually equivalent. So maybe I will give a proof. The proof is simple. So proof. Okay, so maybe 1 implies 2. So what does that mean? So let so this is beta b is v1 v2 vn, so capital V is find dimensional, so I'm assuming that yeah in many elements. Okay, b a basis for v, so the dimension of capital V equal to n. Okay, and let the basis for v. So this is given to us. What is given to us? A is given to us, such that uh, this TV equal to some diagonal matrix say D. Maybe I can write down Dij is a diagonal matrix. Okay, so what does that mean? That is so that thus Dij is what Dij equal to 0 if I not equal to j. Okay, and when I equal to j, it can be anything, and it can be anything, maybe non-zero zero anything. If I equal to j, so I equal to j will give you either 0 or no problem. But whenever if it is not diagonal entries, I not equal to j, they must be 0. Okay, entries are zeros. Okay, that is clear to us. So this is given to us. Now how do we prove that the vector space has a basis whose entries are actually eigenvectors? So from here we will claim that the basis B is actually that basis. Okay, so our claim is what? So claim that this B, which is V1, V2, Vn, is the basis of V consisting of eigenvectors of T, consisting of or containing whatever of eigenvectors of T. Okay, so what we're claiming? We're claiming that this Bi is B1 will be n eigenvectors of T, and that is obvious because from this matrix representation. So what is the meaning of matrix representation? So this Dij, now we call that as, so T of Vj is what? T of Vj equal to summation Dij Vi, right? Because this is matrix representation with respect to the basis B, I equal to 1 to n. But we know that unless I equal to j, it always vanishes, right? So it is always dj, and vj. So what does that mean? That means T of vj equal to dj dj, sorry, djj vj, and this is true for all j equal to 1 2 3 and so on. Okay, so what does that mean? So this is clear that this means that these vj's are eigenvectors corresponding to eigenvalues dj. So thus these vj's are eigenvectors corresponding to the eigenvalues djj. Okay, is clear? So one part we already proved that 1 implies 2. Now we will prove that 2 implies 1. Now 2 implies 1. So 2 implies 1 means what? So we have given that 2 is true. That means your basis consisting of containing all the eigenvectors of T, right? So let's write down that. So let the beta dash equal to some u1, u2, un be a basis containing all basis of V containing of eigenvectors of T. So this is given to me. Now we will show that with respect to this basis T has a diagonal form. So how to show that? Now claim what is our claim? Our claim is that the T with respect to this basis is a diagonal matrix. Diagonal matrix. Okay, this is our claim. Yeah. So now what do you know? So if this is the basis, then what I can write down? We can write down. Uh, so so, uh, so there are two ways to write down. So we can write down for first of all this u1, u2, un are eigenvectors, right? So what does that mean? That means T of say uj equal to or ui whatever, this is equal to some cj uj, right? As uj's are eigenvectors of T, right? So there exists some cj's such that u is equal to cj series, right? But what does that mean? That means you are writing that tuj in terms of uj. So that means that other terms of 0, right? So 0 times u1, 0 times u2, and so on, dot, 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 dot. Only the jth one is ucj, uj. Other than everything is 0, right? Last one is 0 times un, right? So then what is the matrix representation of this with respect to this basis? Obviously the column, the jth column will be only 1 and 2 will be there in the cj, other than that will be 0, right? So then thus the matrix representation of T with respect to this basis B dash will be what? So this will be of the form C1 will be here in the 1 position, then C2 and then C3 and so on, right? Cn. Other than that everything is 0, right? And see, this is a diagonal matrix. So this complete the proof. This complete the proof. Okay. So what does that mean? That means so it doesn't matter whether you choose which is so for finite vector space you can choose any of those things as a definition, and you will have the same result, right? And what is the advantage of diagonalization form? So the advantage is that when you represent something in diagonal form, you can have lots of information. For example, all those that diagonal elements are nothing but the eigenvalues. So you can easily find out that given a matrix is diagonalizable, you will write it diagonal form, and bingo, you get all these eigenvalues. These eigenvalues will be sitting inside the diagonals. But remember that these CIs may not be distinct. There might be repetitions like C1, C2, Cn, up to out of that n maybe 5 are same, 5 C1 are same, then 7 C2, C7 are same, like that. Okay, and some of those CIs may be 0 also. So this is this guarantee does not say that your all the CIs are listing other thing, right? So that can be may not be distinct, right? Okay, but now we are going to discuss one sufficient condition. Under what condition you can say that um, we can say that the diagonal is well. Okay, some sufficient condition are not. Okay, so we need some the important theorems, and this theorem tells you that whenever you have a whenever any linear operator for any linear operator, whenever its eigenvalues are distinct, actually then they actually forms a diagonal matrix to some basis, like that means that is diagonalizable, right? But further I need some theorem, so let me prove this theorem and then we will discuss. Okay, so let same thing. So our my v is given such that so dimension of v is something say n. Okay, and I have a linear operator which is linear operator means map from V to V. Okay, it's elemental LV, and so let so this is given to us. So how do I write down a theorem? I will write down like that eigenvectors corresponding to distinct eigenvalues, distinct eigenvalues are linear independent. Okay, linear independent vectors. Okay, so let me write down in LI. I mean, it's better to write down full form, but I want to save some space. That's why. So distinct means they are different. Each of those are different. Okay. So whenever you have a corresponding eigenvectors whose eigenvalues those are eigenvalues which are distinct, then corresponding eigenvectors must be linear independent to each other. Okay. So proof. So let me start. So let C1, C2, Cn be a set of distinct eigenvalues, distinct eigenvalues of T, and so you choose eigenvectors, say v1, v2, vn are corresponding eigenvectors. Okay, means v1 is eigenvector for eigenvalue c1 and so on are corresponding eigenvalues vectors. Okay, what I need to prove? I need to prove that the V1 will be answer linear independent over F. Okay. So the proof will be, we will do the proof using mathematical induction. So we will use mathematical induction, mathematical induction for the proof. Okay. So mathematical induction. So induction on what? Proof on induction on that degree of the space on n, which is nothing but the degree dimension of v, not degree, dimension of v. Okay. So what happen if n equal to 1? So if n equal to 1, then what happens? Then you have single, right? So then the singleton v1 is always, because v1 not equal to 0, right, is always linearly independent as v1 not equal to 0, because v1 is an eigenvector, it cannot be 0. Okay, so this is done. So for case n equal to 1, our thing is done. Now we will assume that. So now induction hypothesis. What is induction hypothesis? So second step, induction hypothesis. What is that? What we assume? We assume that the theorem is true for any such eigenvalue vectors whose less than n, right? So if you choose any eigenvectors, any number of eigenvectors listing n, sorry, eigenvalue I should say, any eigenvalue less than n, then you are done, right? So assume that the theorem is true for any for n minus 1 many distinct eigenvalues. Distinct eigenvalues. Okay, so this is my induction hypothesis. Now the main statement that what happens if there are n distinct eigenvalues, right? So for n distinct eigenvalues, so let us assume that that this is also true, right? So recall that to prove something is linear independent, what we need to prove? We need to prove that there exists some constant. If the sum of those linear combination is 0, then individual coefficient has to be 0, right? So now let there exists some alpha 1, alpha 2, alpha n belongs to the field F, such that the summation alpha I vi I equal to 1 to n equal to 0. Now we need to prove that all the alpha I is 0, then that will prove that all the vi's are linear independent, right? Okay, so what we do? So we will apply. So now so apply the operator. Apply t minus so Cn of I. So Cn is the nth eigenvalue which is distinct with all the others, right thing. Apply this on this is a 1. applying, probably I should say applying this, we get what we get if we apply this. um, and now we apply this thing, then you will have t minus cn of I of the sum alpha I vi I equal to 1 to n, that is 0, right? Now for linear operator you can do this thing, that so you can write down this as summation alpha I t vi I equal to 1 to n, okay, and then this one is summation cn into alpha I equal to 1 to n, and vi, right? I is identity operator, so the, right? Now recall vi's are the eigen vectors corresponding to eigenvalues ci's for t, right? And then it will apply that results, so that will give you summation. First one will be what? Summation alpha I ci vi I equal to 1 to n, right? And second one will be what? One minute, yes, and second one will be summation I equal to 1 to n. Now check cn alpha equal to cn alpha vi equal to 0, right? Now you see that when I equal to n, you have, when I equal to n, you have alpha n cn vn, and here also you have alpha n cn vn, so that can get cancelled when alpha equal to cn. But other than that, nothing get cancelled, right? So you'll have the sum will run from I to n minus 1, because when I equal to n, the term get cancelled. And what is left? The left thing is that ci minus cn and alpha I vi, that is equal to 0, right? Only the last term get cancelled, right? Now this is the equation of linearly independent vector. So this equation of n minus 1 many such vectors, such that this is, since vi is a linear independent, right? So now you should write down that now by induction hypothesis, that v1 v2 and vn minus 1, so this is linear independent set, right? You have exactly n minus 1 many such linear combination is linear independence over f. So what does that mean? That means that coefficient of this equation must be 0. So thus what we have? We have ci minus cn into alpha I equal to 0, and this is true for all I equal to 1 to n minus 1, for all I equal to 1 to up to n minus 1. Okay, but what does that mean? That means that the c1, c2, cn minus 1, these are all distinct, right? So ci minus cn minus 1 cannot be 0. So thus but as all ci's or cj's are distinct, this is given to us, this ci minus cn cannot be 0 for all I equal to 1 to up to n minus 1, right? So what does that mean? That means this implies that all the alpha I must be 0 for all I equal to 1 to n minus 1, right? So So the first n minus 1 meaning alpha I are 0, but we need to show that even alpha n is also 0, right? But that is obvious. But why? Because we will substitute this in the equation number 1. What is the equation number 1? Yeah, this is equation number 1. Now here you substitute the value of alpha 1 alpha to alpha n minus 1 all up to n minus 1. Then what happened? Now from equation 1, what we get? We get, after substituting these values, we get that alpha n Vn equal to 0, right? But alpha n Vn equal to 0 means what? Vn cannot be 0. Vn is eigenvectors. Again, Vn cannot be 0 as Vn is a eigenvectors corresponding to eigenvalue Cn. This implies alpha n equal to 0. So that's what we prove. We prove that all those alpha 1, alpha 2, alpha is 0. So thus this V1, V2 and so on Vn, this forms a linear independent set, right? Is linearly independent over F. Okay, so this was the theorem. So that we prove that whenever you have a distinct eigen values, then the eigenvector corresponding to the eigenvalues are all linearly independent. So what is the immediate corollary of this theorem? So immediate corollary that tells you that so if you have a linear operators whose eigenvalues are all distinct, then it must be diagonalizable, right? So how do I do? So let you choose T belongs to LV and dimension of V is equal to say n. Okay, so if T has n distinct eigen values, then T is diagonalizable, right? Diagonalizable, okay. And the proof is immediate. So let me write down the proof. So let C1, C2, Cn be n distinct eigenvalues of T, eigenvalues of T, and V1, V2, Vn is the set of eigenvectors of T corresponding to these CIs, corresponding to the eigenvalues right, that C1, C2, Cn. Now the previous theorem tells us that this V1 will be a linearly independent, right? Previous theorem implies that this V1, V2, Vn, these are all implies that this V1, V2, Vn, this, they are linearly independent, right? Over F. Okay. And now see that if you have a vector space of dimension n, so you have maximum n linear independent vector. Okay, so thus this v1, v2, vn forms a basis of v. This forms a basis of v over f. Okay, and now this is one of the definition, right? If we have a basis which is consists of containing all the eigenvector, right? So thus T is diagonalizable. Diagonalizable. Okay, over F. So this is the proof. So this is one sufficient condition. But converse is not true. If T is diagonalizable, that does not mean that the eigenvalues are all distinct. Okay. So maybe we can give some example. Let's see. Okay. Okay. So what are the examples? So what are the problem we have done in last exercise? Maybe we can check in some of those examples. 1 minute. Okay, so okay, maybe we start with the basic example first. Then we'll see other. Okay, so maybe suppose we have a matrix. This T, which matrix form is this is 1 1 1 1 inside R. Okay, so what does that mean? T is a linear operator from R2 to R2, right? It is linear operator from R2 to R2. And so I'm assuming that this is with respect to the standard basis. Standard basis is B1, 1 0 0 1. The matrix will be of this form. Okay. Now, so that means you can easily find out what is the map. Actually, the map will be so T of, you choose a vector v1, v2, and the vector will be what? So you send v1 plus v2. This is also v1 plus v2. This is the matrix, right? Okay, so yes, so obviously you can ask what are the eigenvectors and eigenvalues of T, and how do you check that it's diagonalizable or not? Okay, so let me do one by one. So to check that eigenvalues and eigenvector, you need what? You need the characteristic polynomial, right? So the characteristic polynomial, polynomial of T is what? So let me write down fx equal to determinant of x into I, identity matrix minus that matrix and T. Okay. So you can write down that xi means x0 0x, and T is what? 1 1 1 1. Well, what is this? This is x minus 1 minus 1 minus 1 x minus 1 x minus 1, right? So determinant will be what? X minus 1 whole square minus 1, so that means x minus 2 into x. So this is the characteristic polynomial, x minus 2 into x, and hence the eigenvalues, the eigenvalues of t are so it means x minus 0 actually. Okay, so are 0 and 2 which are distinct, right? So thus t is diagonalizable, right? We just prove it. Okay, now question is that if it is diagonalizable, then what is the diagonal matrix? So diagonal matrix, we know that diagonal matrix will be of the form, so the eigenvalues will be that eigenvalues will be that entries, right? So that means there exists some basis b such that t of b, this has to be of the form this 0 0 0 2, right? Yes, because the eigenvalues are 0 and 2, so that they will be in the diagonal other element is 0, right? Now what is the basis? The basis will be the corresponding eigenvectors, right? So you choose eigenvectors now. So what are the eigenvectors? If you choose, so for example, suppose we want to find out the eigenvector corresponding to eigenvalue 0, so it will be 0 times v1 v2. So what is that? This is nothing but 0 0, and this side t v1 v2 is what? So this is 1 1 1 1 and v1 v2, right? Which is nothing but 0 0 column vector. Now here you have v1 plus v2 and v1 plus v2. This both will give you same equation, and equation is what? v1 plus v2 has to be 0. So what does that mean? That means v2 equal to minus v1, right? So the eigenvalues are what? So eigenvalues, so thus the eigenspace, so eigenspace we define corresponding to 0, that is what? That is collection of all v1 and minus v1, right? Of this is that v1 not equal to 0. This is sorry, I should not say v1 not equal to 0. Eigenspace also contains 0. So what should I say? Yeah, so v1 belongs to this v. Okay, so what does that mean? That means e naught is actually generated by, so this is what? This is v1, not v2, because v2 equal to minus v1. Yes, so this is means what? This means this is v1 times minus 1 minus 1, right? v1 belongs to v. What does that mean? That means it is generated by the vector 1 minus 1. Okay, so this is one vector, we just got it. Okay, and then for E2 also for so these eigenspace are actually, see, remember what we defined. This we defined that for eigenvalue C, the eigenspace is of this form: all the V belongs to V, such that TV equal to CV, right? But that means what? That means all the V belongs to V, such that T minus C of I of V equal to 0, right? But this is what? This is nothing but the null space. This is nothing but the null space of T minus Ci. Okay, here I just find out the null space of C, and when C equal to 0, null space of T. What is the null space of C? In the kernel of T. That is actually added by the single vector. Now similarly, you have to find out null space of T minus 2i. Now how to find out null space of T minus 2i? So again, so obviously you can either directly find out by definition or whatever we are doing by that method, same method, that for C equal to 2, we can find out that T into some V1 V2, that will be 2 times V1 V2, and that tells you that V1 plus V2 and V1 plus V2, that will be equal to 2V1 2V2, right? Now from this you have the same equation. No, there are two equations. Yeah, so from first equation, what do you give? V1 plus V2, V1 plus V2 equal to 2V1, but that implies V1 equal to V2, right? From second equation, you have V1 plus V2 equal to 2V2, but that also implies V1 equal to V2. Okay, so what does that mean? That means the eigenspace is actually generated by the same, so both the entities are the same, V1, right? V1 belongs to V. So what does that mean? That it is generated by the vector 1, 1. Okay, so thus you have now new basis B dash, which is equal to, so first one was what? First one was 1 minus 1, then 1 minus 1, then 1 1. Now you see that this basis is basis consisting of eigenvectors of the map T, and hence this diagonalization, right? But we need to say that with respect to this basis, this forms a diagonal matrix. Then we are done. So with respect to this, how to form that? With respect to this forms a diagonal matrix. T forms a diagonal matrix. You need to check that how, if you, if you want to find out the diagonal matrix with respect to this basis, what do you do? Change the basis vector, you need to multiply by that, right? And now okay, so the matrix, okay, so 1 minute. Or we can do from this itself. Okay, so there are two ways. You can find out the change of basis matrix and multiply that T Q inverse A Q and find out that this is actually of that form, or you can directly find out the matrix representation with this basis. So then what you do, you do that, you find out T this. Okay, so see, I'm writing, but this would be actually 1 minus 1, this column vectors. So what will be column vectors of this form? So you recall that T is sending V1 V2 as V1 plus V2, right? Yeah, so T is sending V1 V2, V1 plus V2. So this is 0 0, right? So this vector is T sends 0 0. So what does that mean? That means this is 0 times 1 1 plus 0 times 1 1 with this basis. Now the other one is T sends 1 1 to 2 to 1 plus 1 1 plus 1, right? 2 2. But 2 2 means what? 2 2 means that 2 times 1 1 plus 0 times 1 0, right? So that matrix representation will be what? So matrix representation with respect to the basis B dash will be what? It is 0 0 0 2. See, this is exactly the matrix what we are talking about. Okay, so what does that mean? That means that with respect to this new basis, which consists of eigenvectors, you will have a the matrix representation of T will be a diagonal matrix, and is the diagonal entries are exactly the eigenvalues. Okay, eigenvalues of the linear operator T. Okay, now this is one way I just showed you. Now I am giving you homework to find out the other way. Other way means that you just do the change of basis matrix from the basis B to B dash and check that that T B dash is also this. And further you need to find out the matrix Q, right? In this change of coordinate matrix Q, so that you can write down Q dash Q inverse T TB into Q, that will be TB dash. Okay, now find out that will be, maybe let me just do it one by one. Let's see how as it goes. So for example, if you want to write down okay, so 1 minus 1 in terms of the basis 1 1. So what do you write down? You write down 1 times 1 times 1 0 and minus 1 times 0 1, right? and if you then write down 1 1 1 times 1 0 1 times 0 1, right? So that matrix Q will be 1 minus 1 1 1, and this matrix is obviously invertible matrix. The determinant is non-determinant. What is determinant of this Q? Determinant of Q is 1 minus plus 1, so 2, right? So what will be the Q inverse? Q inverse will be 1 1 and 1 minus 1. This is Q inverse. Okay, so Q inverse, right? Now to multiply this by the given matrix T, Q inverse TQ, then what happens? So Q inverse TQ 1 1 minus 1 1, and then 1 1 1 1, and then 1 1 minus 1 1, and let's see what happens. So I am multiplying this. Sorry, Q inverse. So this is inverse. This is plus minus. Okay. So multiplying these things. So A 1 into 1. This is 0, and then this is 0. This is 2. This is 2. Then 1 1 minus 1 1. If you multiply by this, then what happens? 0 into 0 0 into 0 2 into 2 is 2. 2 into minus 2 0 0 2 into 2 2 plus 2 into 2 2. Oh, no. This is sorry. This is 1 by 2 times this. Determine 1 by 2 times the determinant of that thing. Yes, that's why this is a problem. This there should be 1 by 2 here. Yes. So this 1 by 2 times this. Because 1 by 2 is the determinant of Q. So you have to divide by the determinant, right? Now this is 2 plus 2 is 4. Now you multiply by 1 by 2, then you will have 0 0 0 2. Now see, this is exactly the matrix representation with respect to that new basis PV dash, and this is TB. Okay. So so anyway we have checked with all the method, and this is X. So whatever method you can find out, you can use it. Either you can use it by the changeability matrix, or you can use the direct definition from that matrix with respect to basis B dash. Everything is possible, and you check that for everything the answer is correct. Okay. So this is one such idea of diagonalization. There are many ways you can do it, and we will do it in our next 1 or 2 lectures maybe. Okay, so today I am going to stop here. Okay.